Large language models operate on semantic probability, constructing abstract logic by predicting the next token in a linguistic sequence. A bipedal robot navigating a factory floor must calculate gravity, momentum, and spatial geometry in real time to maintain its balance. Historically, developers addressed these requirements by chaining together multiple specialized single-modality systems. This requires a vision language model to parse the environment, a diffusion model to simulate outcomes, and a policy network to generate actions. This handoff creates delay. Latency spikes as data translates across disparate networks, misaligning what the robot perceives and how it moves. For autonomous agents, this multi-system orchestration remains the primary obstacle to achieving real-time physical reasoning. Released at Computex 2026, NVIDIA Cosmos 3 addresses this fragmentation as an open omni model engineered specifically for physical AI. It natively processes text, high-resolution imagery, video, ambient sound, and precise robotic actions within a single system. Standard generative video models often prioritize pixel-level aesthetics, creating realistic visuals that can still violate the laws of gravity or structural consistency. Cosmos 3 ensures physical accuracy by synthesizing every input modality through a unified forward pass, removing the need for a chained pipeline of separate models. By combining logical reasoning and physical imagination into one architecture, the system provides a singular foundation for both perception and action. Before input data reaches the transformer backbone, it is compressed and translated through a specialized tokenization layer. Standard video tokenizers compress a present frame by pulling data from both the past and the future frames of a clip. This approach fails in physical AI deployments. An autonomous vehicle cannot access sensor data from 5 seconds in the future to make a navigation decision in the present. The NVIDIA Cosmos tokenizer utilizes 3D causal convolution blocks to process spatial and temporal details jointly. It enforces causal temporal attention, restricting the tokenization process to only past and present frames. Any future data is inaccessible during the compression phase. Once the temporal constraint is set, the tokenizer applies 3D wavelet downsampling. This signal processing technique eliminates redundant pixel data, allowing the neural network to focus exclusively on meaningful physical features of the environment. This architecture delivers 8 times more total compression and processes data 12 times faster than previous standard tokenizers. Enforcing causality at this fundamental level ensures the model's internal logic mirrors the unidirectional flow of time in the real world. To process these compressed tokens, the system must map disparate modalities, pixels, audio, and motor commands, into a common mathematical framework. Specialized modality encoders handle this translation. Vision transformers extract deep visual understanding, while variational autoencoders are used for visual and audio generation. Domain-aware vectors are simultaneously used to encode the complex robotic actions and kinematic coordinates required for motion. These specialized encoders all output directly into a single shared representation space. By forcing visual data, ambient sound, and motor commands into a shared latent space, the model avoids the data loss that occurs when translating information between isolated systems. Inside the mixture of transformers, or MOT, backbone, the system splits the shared representational data across 2 distinct computational paths. This 2-tower configuration is designed to separate the analytical process of reasoning from the generative process of imagination. The reasoner tower uses an autoregressive transformer architecture to act as the analytical center of the system. This tower is optimized for spatial grounding, physical reasoning, and establishing the causal relationships required for multi-step task planning. The generator tower utilizes a diffusion transformer pathway for iterative denoising. Conditioned on the reasoner's logic, the generator produces physically accurate video frames and precise robotic action trajectories. In a guided forward pass, the reasoner establishes the physics and meaning of the scene, which the generator then uses to synthesize the visual and motor output. These towers stay synchronized through joint attention. This mechanism forces the separate parameter sets of the reasoning and diffusion blocks to interact constantly across every transformer layer. This continuous interaction binds the generative process to the analytical process, ensuring the final output adheres to the model's logical understanding of physics. Deploying a massive dual-tower architecture for real-time reasoning is notoriously compute-intensive, often exceeding the limits of commercial hardware. NVIDIA engineered several distinct architecture scales to make Cosmos 3 compatible with different industrial deployment scenarios. The 64 billion parameter super variant is designed for data center simulation, while the 16 billion parameter nano variant is optimized for workstation-grade GPUs. To improve efficiency on smaller devices, Cosmos 3 supports native sub-8-bit quantization on the Blackwell architecture. 4-bit floating-point quantization compresses the neural weights while maintaining mathematical accuracy, yielding up to a 2x acceleration in inference speed. This is paired with efficient video sampling, which prunes redundant data at the token chunk level to lower compute pressure during vision-language reasoning. These optimizations allow the model to deliver data center-grade physical reasoning on untethered edge robotics. This efficiency enables the Cosmos 3 architecture to function as the backbone for world action models. A world action model takes a static observation and a task instruction, then predicts both the future visual state and the necessary motor actions simultaneously. This enables forward dynamics, allowing a robot to imagine the precise physical outcome of its proposed movements before moving its physical hardware. To encourage commercial adoption, NVIDIA released model weights under the OpenMDW 1.1 license from the Linux Foundation. This permissive license allows organizations to train, modify, and deploy Cosmos 3 commercially without field of use restrictions. By combining an open legal framework with an architecture that respects physical laws, Cosmos 3 operates as a digital imagination engine. It allows robots to fail millions of times in causal simulation, closing the gap between virtual training and real-world execution.